So now let's apply what we've learned about sampling distributions. First, I'll mention that we can find z-scores for the sampling distribution of the sample mean. That looks similar to what they did for the population. So you've got an individual sample mean minus the mean of the sampling distribution divided by the standard deviation. Most of the time we won't need to do that because we have technology that will compute probabilities for us. So according to the National Association of Realtors, average home price in the first quarter of 2016 was $180,100. Standard deviation was $4,500. So if an individual home is randomly selected, what is the probability the price exceeds $182,000? So they are asking here, what is the probability that X, an individual home price, is greater than $182,000. So, well, if we know that things are normally distributed, so if we know the population is normal, so I have to make that assumption. So, assuming the population is normal, then we can use normal CDF. So this will be normal CDF. And then our lower bound, 182,000. Our upper bound, infinity. We could just use a very large number, like 1 times 10 to the 10th. So in your calculator, that'd be 1e10. And then our mean was 180, 100, and standard deviation 4,500. So let's go ahead and compute that on the calculator. So second variables, go to normal CDF, number 2. Our lower, 182,000. Our upper, I'm going to do 1, and then the EE, so second function. So that's times 10 to the 10th. Mean, 180, 100. Standard deviation, 4,500. Paste it, 0.3364. So assuming that the population is normal, then be a 33% chance that an individual home price would be over 182. Now, if a random sample here, sample of 45 homes is taken, and the average of their prices is calculated, this value belongs to what distribution? So if you take the average of their prices, that is an X bar value. So this is in the sampling distribution of the sample mean. And it's for n equal 45. What's going to be the shape of that distribution? Well, n, which is equal to, if there's samples of size 45, that is greater than or equal to 30. And so by the central limit theorem, that implies that our distribution is approximately normal. And then lastly, we want to know what is the probability that the mean of that sample will be greater than the 182. So this is asking what's the probability that X bar, a mean of a sample, is greater than 182. So our distribution is approximately normal because n is big enough, so we can use normal CDF here. And our lower cutoff the same, 182,000. Our upper cutoff, we'll use the same, 1 times 10 to the 10. our mean is the same, 180 and 100. But then our standard deviation changes here. Remember that the mean of the sampling distribution is the same as the mean of the population. Which is that 180,100. But then the standard deviation of the sampling distribution, sigma x bar, is sigma over root n. So that is going to be our 4,500. And then we divide by square root of 45. So let's compute that on the calculator. So 670.82. And that's what goes in the last slot. So let's go ahead and compute that. So this will be second variables. Number 2 for normal CDF. Lower and upper are the same. Means the same. But now our standard deviation, 670.82, correct? Yes, 670.82. Paste it, enter 0023. So much smaller probability that the mean of a sample of 45 houses would be greater than 182,000. And that makes sense. It's going to be easier for one house to be greater than the 182 than for the mean of a sample of all 45 houses to be greater than 182. So just be careful, when they're asking about probabilities of means. The mean of the sample, that is an x bar value. That means that you're using the sampling distribution. You have to adjust your standard deviation.